Good evening, everyone. I welcome you all for today's session. So, I believe everyone has joined. Okay, so we'll start the session. It's time. Okay, so a very warm welcome to all. So, before starting the session, on behalf of Chipesh team, let me wish you all a Merry Christmas and a very happy and healthy New Year ahead. Okay, so I feel privileged to welcome you all on behalf of Chipesh Technologies for today's webinar on latest trends and challenges in physical design and career opportunities. So before starting the session, let me introduce myself to you. I'm a DFT engineer working in Chipesh Technologies and I'll be initiating today's session. So to begin with, Chipesh Technologies. Chipesh Technologies was founded in October 2012 by Mr. Venkat Sunkara, the CEO, as a VLSI skill development company to bridge the gap between industry and academia. As we all know, over the years, Chipesh has grown to provide comprehensive VLSI courses in digital and analog domains, and today, Chipesh is one of the leading VLSI training institutes. And the CEO, Mr. Venkat Sunkara, has over 22 plus years of experience in VLSI industry with a mix of design and application engineering experience. He started Chipesh Technologies in October 12 as a skill development company to bridge the gap between industry and academia. Before starting Chipesh, he was with Cadence Design System, Bangalore, and was responsible for synthesis solutions. He worked with Time to Market Private Limited, Hyderabad, and was responsible for physical design projects. Before moving back to India, Venkat was with Cadence Design Systems and was responsible for synthesis solutions. He started his career with Colcore Logic Private Limited, Hyderabad, and was responsible for FPGA to ASIC migration projects, which involve synthesis, STA, DFT, validation, timing simulation, and formal verification. He is a member of Talent Core Initiative Committee in India Electronics and Semiconductor Association and contributing in skill development initiative in electronic system design and manufacturing sector. I welcome you, Venkat, for the session. Next, our COO, Prasad, is also a part of this webinar and he is having an experience of 20 years in operation management. I welcome you, Prasad.
Thank you, Nikita. Thanks a lot.
Okay. Today, Venkat will be sharing his thoughts and industry experience on latest trends and challenges in physical design and the career opportunities in physical design. Now, once again, a very warm welcome to you all for today's session. And I request Venkat to take over from here. Over to you, Venkat.
Okay, so the latest trends and challenges in physical design and career opportunities. Here is the agenda overview of VLSI industry. I think in the overview, I will have to repeat some of the slides because many of you are new. Those who are joined last week has to bear with me for the initial slides. But then after that initial slides, I'll switch to physical design and physical design flow, trends and challenges in the physical design, career opportunities for physical design in the VLSI industry, question and answers. So we have put together a small demo also. So with the tool to show you how this physical design works. So it's all more about physical design. What is this specialized about, and what it covers, how it happens, what are the career opportunities, how the nature of work involves. We'll try to cover that a bit. But the challenge I have is the time. Ideally at least half a day to 1 day is required to cover this. So to cover that in 1.5 hours is a challenge. So it's not easy. Hence, I may go slow speed in some places. I may skip some slides because lack of time. I'm not sure whether we'll be able to. If we find time, we'll go into physical design demo and we'll try to squeeze some time for the demo part. Okay. Now let me start with I think some of you, as I said, some of you already familiar, need to bear with me on these slides, initial set of slides. But however, I'll quickly go through the applications of electronics. We know electronics is everywhere. Without electronics, nothing, whole world, stops working. That much, dependent on electronics today. The whole world in every application, starting from, consumer electronics to medical, mobile, aerospace, and aerospace, you name anything, every sector depends on electronics. And if you look at the components of iPhone, any iPhone or any mobile, you have so many electronic chips in that iPhone, in that, one is processor, memory, and you have a controllers, you have Wi-Fi chip, you have a Bluetooth chip, and all of that. So which are all nothing but semiconductors. So nothing but semiconductors. So if you take let's take a mobile processor. Typically, most of you are familiar with the Snapdragon processor of Qualcomm. So the Snapdragon is a SoC, system on chip. This is the architecture. This is the architecture. It has many, it is a heart of the mobile. It's a heart of the mobile, doing many things. As you can see, it is interacting with the audio, video, signal, the storage, camera, so many things. As you can see, battery. So this is the architecture. It has a memory, it has a modem, it has a CPU, it has a GPU, it has a display controller, DSPs, video controller, so many things, doing so many things. Hence it is called SoC, system on chip. Hence it's called system on chip. System on chip. Earlier it used to be a big motherboard. Nowadays it's a small single chip doing different things. Nowadays even Qualcomm went up to this is the latest generation that Qualcomm is shipping now, 5G 888 model, and 88 plus S model has come. It has the very latest features of camera, artificial intelligence, security, connectivity, gaming, you name anything, and you know all of that, right? So semiconductor industry is a collection of companies engaged in design and fabrication of semiconductors, like Intel, laptop processors, i7, i9, AMD, Qualcomm, Snapdragon, NVIDIA graphics card, Broadcom Wi-Fi chip. Broadcom is popular for Wi-Fi chip, Bluetooth chips kind of, and other things. So semiconductors is essentially enablers that they power the many of the cutting edge devices, digital devices we use today. And out of all semiconductor, MOSFET is the core and core or the primary factor behind this revolution. I mean, hence the MOSFET, the core technology used, which is the reason behind this technology growth, or technology miniature, the year on year, the improvement in technology is an improvement in MOSFET technologies, MOSFET fabrication, right? Is the driving behind the semiconductor industry. I mean, so I'll come to that a bit little later. So from here onwards, that's about previous. Here onwards, I'll spend some quality time. So I think I covered this last week also. ASIC design flow, how a application specific, ASIC means application specific design flow. So as I said, for your information, mobile Snapdragon mobile processor is a application specific chip. So it cannot, when you say application specific, let's say, can you use mobile processor for a laptop or a tablet or for a watch? No, you can't use it. Even you can't use a Snapdragon suddenly into an iPhone. You can't use it, because the how it is designed for Snapdragon, it works on Android, not on Apple iOS. Of course, the particular, once it is designed for a particular, let me put it this way: it's designed for mobile application. It cannot be used for other applications. It's designed for certain model, certain feature. Let's say a 5G chip cannot be used, a 4G chip cannot be used for 5G, because the design is different. That is the reason now they say you have to upgrade to 5G if you need a 5G signal, something like that. So application specific means you cannot use it for other purpose. You cannot use it for, as I said, laptop, tablet kind of it. So how a ASIC or a particular chip will be designed, this is the flow. Design specifications, then RTL design. This is where the designers will code in. Initially, the system architects will design the specifications, hardware, software architecture, what new features need to be added, which team will develop that, and what is the power requirement, low power requirement, what is the speed, which frequency this new version of the chip, 5G, let's say 5G, has to work. And they will decide. Then they will plan the microarchitecture, and then the design teams will start working. RTL teams will start working in a Verilog system, Verilog. They'll start coding the design into different blocks, functional as per the functionality. Then functional verification or design verification team. Here comes the design verification or DV design verification or DV. This team comes and verifies the functionality of the chip, whether it is working at a 5G, let's say if it is Snapdragon 5G, is it working at a 5G? Is it receiving 5G signal or not? For receiving and transmitting, is it doing it well without hiccups, without bugs? So functional verification is nothing but a testing in software terminology. There's a software as a manual testing, automating testing, right? It's nothing but a testing, but it's a testing for functionality. Functionality means for which the chip should work. So that is about functional verification. So there will be iterations between design team and verification team until the code, works 100% as per we spent on this. The once it is working, let's say 100% chip is working at a code level, software at a code level, Verilog system, Verilog level, then they say, okay, now code, we are at a software level, it is working. Now let's think about manufacturing this chip at a particular foundry. Then they will think about synthesis. Let's say this synthesis, I don't know if my cursor is visible. Ideally, I wish I have a pointer or a laser to point out. I'm at a third block, synthesis. So synthesis, from here starts the technology related work. Which foundry we need to manufacture. So let's say whether it is TSMC or Samsung foundry, 7 nanometer, 5 nanometer, then when all this remaining work is foundry related. So which means you can see most of the design time is spent in the foundry related work only, to how to make it manufacturable, how to make the design manufacturable, because so many steps are there and that's a long process. So design is one part only, design and verification. After that, so much synthesis, DFT, physical design. So remaining sign off, timing and verification, fabrication, packaging and testing. Then the chip will come out. So I will take as the focus is the physical design for this webinar. I will spend some time on more time on what is synthesis, what is physical design. I will spend some time. So if you look at on the right side, so for all of this work to do, starting from step 1 to last step, every stage involves a lot of softwares. In VLSI, it is called EDA tools. VLSI tools, or it's called EDA tools. Cadence, Mentor Graphics, Synopsys are the EDA companies who offer different softwares for the semiconductor industry. This one on the right side, if you see tools for synthesis. Tools for synthesis, Synopsys Design Compiler, Cadence, Zenus. Tools for physical design, Synopsys, Cadence. Tool for timing sign-off, Synopsys, Cadence. So primarily this area, Synopsys and Cadence are leaders in this space. Tool for physical verification, Synopsys, IC Validator, Cadence, and Mentor Graphics is the leader in a physical verification. So typically you need to have one of these tools to do a physical design as an industry standard. So tool is a must. Tool or VLSI tool or VLSI software is a must in a VLSI, and these are typically very costly. And physical design, these are the steps. In this a bigger flow, the physical design is a one particular specialization, and that involves bunch of steps, as you can see on the right side, right? Now I will go a little more into the physical design flow. So let's dig in. Let me take into a little more deeper into physical design. What is physical design? Physical design. See, there's a word called physical. Physical means from here onwards comes the manufacturing part of the design. Manufacturing part. Physical. Like, metals, CMOS diffusion layer, the CMOS fabrication, then metal connectivity, the signal connectivity through metals, and all of this comes. So it starts with a design import. Design import, I mean, you load into the tool. So the reason for VLSI so costly, VLSI courses, the salaries for VLSI are high. The reason for high salaries or even courses are costly, the reason is that these VLSI tools are very costly. Let's say physical design tools which are mentioned in this previous slide. Let's say tools for physical design, IC compiler 2, Innovus. These are not less than $1.5 lakh one license per year. $1.5 lakh license, which means you can say 1.2 crores for one license per 1 year. IC compiler 2 or Innovus. 1.2 crores for one license 1 year. Right? Hence, this is very costly. That is the reason VLSI tools are very costly. If they want to give that tool to you to make a PD engineer, then you should be using the tool smartly, because it's 1.2 crores. If you are wasting the time of the tool, then you are wasting the money of the company. Hence, the VLSI industry looks for smart engineers, not like just who knows. With a strong, smart engineers who are good in fundamentals, who have a good analytical and reasoning skills, who understand the concepts. They cannot. That's why they are very particular about hiring. Now, coming to these are the different steps. Just to understand what are these. So you may not understand everything now, but I will try to take a little bit into the. Maybe you will understand better if I show through a demo. So before synthesis, right? Nowadays, synthesis is part of the physical design. So let's see what is the physical design. What is synthesis? Let's say you have I believe you should be able to understand this. Let's say you have a Verilog code, assign out1 equal to in1 and in2. It's a assign AND gate, right? It's a code, Verilog syntax for an AND gate. This is the construct, Verilog construct. Let's say this is your Verilog file. Now, this is a chip now. You want to fabricate it, right? Now, fabricate it into Samsung 7 nanometer, let's say, right? Then you need to target this 7 nanometer of Samsung. And when you do that using synthesis tool, when you give that Samsung 7 nanometer library to synthesis tool, you get an AND gate 4x2 and this one AND gate 4x2 C126 A1 A B Y. So, and then if that AND gate is working at required frequency of 2 gigahertz or 1 gigahertz, and is it having enough low power where it doesn't it doesn't consume more battery, and is it consuming less silicon area? If it is good, then they will they will send it to physical design team. So earlier synthesis and physical design is a separate team. Nowadays they are same. You are a physical design engineer, you should be doing synthesis also nowadays, unlike earlier. So synthesis is a automatic method of converting higher level of abstraction, lower level of abstraction. In other words, an RTL level design to gate level netlist is the purpose of synthesis. So it is a tool driven job, and the output will be sent to physical design. So this is still a synthesis, different steps in synthesis. Let's say your input is RTL code in Verilog. Then you have a timing constraint, what frequency it should work. Then you have a different input files library. These are foundry specific files. Technology related inputs are foundry specific input files. Then you give this synthesis tool. Even synthesis tool is also very costly. At least $75,000 to $1 lakh $75,000 a year. Not easy, costly, very costly. So the tool will do it. It will convert to gates, as in the right side. The output is a gate level netlist, and it will optimize your logic. As you can see in the right side, a NAND gate. If you provide some code, it will provide a gates. So instead of, in other words, it will provide a behavioral, it will convert your behavioral Verilog to structural Verilog, those who are from a Verilog language point of view. Now, initially you have a code, now you have a gates in the Verilog file. I will, something like this, yes. So if you have a code like that, and internally it will map to a Boolean, generic gates. After that, technology specific, Samsung 7 nanometer, it will map. This is what happens. This is what happens inside. This is what happens inside. To produce a netlist which meets below goals: timing, area, power, routable. So timing means frequency, as I said, area, power, low power. It shouldn't consume more battery because we want more frequency when we purchase a mobile. We want a better backup when we purchase a mobile. We want it to be very sleek and good looking. And all these we want, hence the companies will target for that. Otherwise, they cannot compete in the market. So what is physical design now, right? Let's say a physical design is a process of transforming a circuit description into physical layout. Let's say you have a CMOS inverter like this, which is a PMOS, which is a combination of PMOS and NMOS transistors, right? Now this is a transistor level representation for us, for our understanding. But ultimately, this has to be manufactured, right? If you want to manufacture a chip or an inverter, it has to be a CMOS level, CMOS substrate, CMOS diffusion, P diffusion, P N channel, and the gate, and then the base, right? So it will transfer. It has to be transformed into a layout view for fabrication. First, diffusion, then the poly, then the contacts, as you can see on the right side. Otherwise, you can't manufacture it. Ultimately, this is not a software. VLSI, it is not a software. You have to have a chip which is a hardware. So we need to send the files in such a way that they can be fabricatable, manufacturable. So circuit description into the physical layout, which are manufacturable geometries. That is the purpose. So the gate level representation to manufacturable geometries we need to convert. That is the purpose of physical design engineer. You will not design this one, you will physical design. You will only convert your design a fabricatable format only. How the describes the between them. During physical design, all the design components are instantiated with the geometric representations. In other words, how the memories are connected, how the cells are connected, how the gates are connected, transistors are connected, kind of. So impact of physical design on circuit performance. Yeah, I think if you look at the performance means frequency. Long routes have significantly longer signal delays. Area, placing connected modules far apart results in larger and slower chips. I think I'll skip that for your, I think that will be too much for you. So this evolution of physical design, nowadays it was called physical design. 20 years back, it was called layout. 10 years back, it was called, 20 years back, it was called PNR, place and route. So 20 years back or much earlier, it was called IC layout. So it was getting transformed. It is becoming a more and more specialization, and it is taking significant amount of time in the design cycle. As the transistor MOSFET technology, MOSFET manufacturing technology is improving and improving, then the new challenges comes, and every technology has to go through the physical design, every chip. So hence physical design has become a more dominant and more in-demand skill in the market. Let me see before going on. Let me take some questions. Sir, will you cover how to perform each step in the tools? Yeah, I have planned a demo because live we felt like it will take. See, if I take a bigger, it will take one step will take even if I take a smallest design, it will take few minutes, 10 minutes, 5 minutes. That is the smallest. Typically, it will take hours. Bigger design. So we have taken a smaller design. But even then, to give a live demo, we felt ideally this should be a half-day workshop or one-day workshop. 1.5 hour webinar is too much. We can't do ideally, we would love to. So we have recorded that, and that is available with me. In the interest of time, I will try to show if time permits. But we would love to give a demo. So let me spend some time on that. Which domain we can learn fastly? All domains are nothing in VLSI is just like that easy. Like each is a specialization in VLSI. Whether you take design verification, whether you take design for test, physical design, anything. Each is a specialization. Nothing is fastly. It's not like that. Is there any open source tools for the same? Open source tools maybe there. See, as I said, right? Open source tools. See, the point is technology is changing at a faster rate. 7 nanometer, 5 nanometer, 3 nanometer. There's so much complexity. Open source tools will not be able to catch up with that complexity because it involves a lot of investment from R&D engineers. So it looks like there are open source tools, but for taping out, for production purpose, they will not be used because they can't handle, and the time availability is less. Time availability is you have to release the chip in 6 months, and so the tools has to support for that purpose. Only then they will be in the market in competition and with the competition to others. Front end and back end. Is there any front end and back end in VLSI? So I think it used to be, people used to call front end and back end in VLSI earlier, but not nowadays. The reason is there are boundaries has vanished. Boundaries have vanished of late, unlike earlier. Okay. So I'll take the remaining questions later. I will switch to my. Did I stop sharing? Wait a minute. Are you seeing my PPT, Prasad, still?
No, Venkat.
Acha.
You need to share that.
Okay. I will continue. So let's say we want to, construct a house, right? And then what we will do, we will decide, we will go to a civil architect and ask him, sir, please give a design for our house. We want to, this is our space available, this is how we want a 3-bedroom house, duplex house, or we want where the kitchen is, where the entrance is. We will ask for a plan, and they will give a plan like this for the space available for your space, literally physical space available, and as per your requirement, the civil architect will give a plan like this, right? Bedroom, where the bedroom should be, where kitchen should be, and all of that. Right now, living room should be, where door should be, window should be, all of that. And with you have a square, 40 by 40 square feet by 60 square feet, site. If you have, you will get a plan like this. So similarly, in a physical design, in a VLSI space, there is a term called floor planning. You will plan your die, wafer or a silicon die, how your chip area, how you plan your chip, how effectively utilize the silicon area for manufacturing your chip. It has to be effectively utilized because it is a bulk production. IO initialized for planning, IO port placement, macro placement, physical. So there is a these two are comparable. For our example, if you it will be easy to understand if you oh, wait a minute, my audio. If you let me show you next slide. The left side is your house floor plan. It's a floor plan, and you give once you get a plan from your civil architect, you will give that to your construction manager, or nowadays in a the person who does the civil works, or mestri in our terminology we will call, where you will start as per this plan you will start constructing the pillars, you will start constructing the walls, then slab, then that is the first structure, first as per that plan. Similarly, on the right side, our chip, the whole chip should be whole functionality. Let's say you have a CPU, you have a GPU, you have a clock generating block, you have a as you have seen that Snapdragon processor, right? You will have to accommodate all DSP. You have analog blocks, you have digital blocks. This is how a chip should be. Why this, right? These blocks, these are different blocks, means different things, different, let's say CPU, GPU doing different things. In a silicon or physical semiconductor space, we call that a die on which you will fabricate the chip. In fact, I have a video, but if you have a time, we will play that. Room floor plan, block floor plan. So this is how a room level, right? In room level, you will decide where the table should be, where the bed should be, where the cupboard should be. Similarly, in a block level, we'll decide which side should be which memory, which side should be clock generator, and all of that. So this is how the reason is nowadays, as the real estate has become very costly, that is the reason people are constructing, because it's your physical land is very costly, site is very costly, and people are constructing apartments. Earlier it used to be 4 floor, 5 floor, now 10 floor, 20 floor, 30 floor has becoming a more of the trend nowadays in depending on the city. Similarly, in the chips also, as more chips has to be manufactured in a bulk, in a process, hence in a smaller the area and more metal layers, like the 14 layers, 19 layers, metal layers. Chip is vertically going up the way you construct the apartments, many flats into one building. So these are called macros, means memories. Macro means which is already pre-designed. It could be a PLL, it could be analog to digital converter, digital to analog converter, or it could be a ROM, RAM, anything which is already designed and will be used here. And you will not, it is a fixed size and width. So now, so far, once you come to physical design level, you don't see OR gate, AND gate. You only OR gate, AND gate will be in the form of width and height, because only in a CMOS fabrication, right? What is the width it will take? What is the height? No more graphic, no more gate level, schematic level representation. It's all physical. I don't know how much you are able to understand. Try to understand to the extent possible. It is. If not, we will see. Don't worry much on that. I'll try to give a demo on that to the extent possible. Full chip floor plan, partition. This is how a physical design view will be. As a physical design engineer, you will work on. This is a chip level. How it will be a physical design chip will be core. IO cells means input output pins. So because it cannot be, a pin cannot drive. There should be a buffer or a strong driver to drive a signal. Power plan is basically, when you have a chip, right, you should have a power, and power in this case is a DC, and that should have a VDD and VSS. Every cell, every gate in the design should get power. Power in the case, you should get VDD and VSS, and your memory should get, Every block, your RAM should get this one, your clock generator should get power. This is how it's called power planning. Once you plan the floor, you should, in a house also, right? You will plan your power where, let's say for fridge, for a grinder, for a mixie, you give a 3-pin plug and 16 or 20 amps switches. For a normal tube light, fan and all of that, you use a normal line. So similarly, the way you plan power signals, power wiring in the home, we'll plan a power signals for the chip also, because all signals should get power equally for it effectively function. So that is about power planning. Then we call the placement in the physical design flow. Let me see if I have a placement is a kind of placing your gates, AND gate, OR gate. We call a standard cells. Standard cells. AND gate, OR gate, flip-flops, latches, all these are called standard cells. It's kind of think like this. Let's say you have a bricks, right? Whichever room it is, you still use a different bricks and they cut into different size of bricks to construct the wall. So it's a units basically. AND gate, OR gate, inverter, buffer, flip-flop, all these, using those gates your design will be built, right? So that's what they'll use it here to physically place. Perhaps you will appreciate only when you see a demo or real representation. Clock tree synthesis. Venkat, okay. So the demo to provide, but Venkat Kamal may not have the access, right? That's okay, I'll manage. Prasad, I was thinking to give a demo. If Venkat Kamal can present, but he may not have control to present. So I'll manage that. So let's say you have a flip-flops. FF1 means flip-flop 1, flip-flop 2, flip-flop 3, like this. Then each flip-flop in the design should get a clock uniformly. Let's say you have a 10,000 flip-flops in the design. 10,000 flip-flops should get a clock at the same time. With a few picoseconds, delay is acceptable, but not, more skew, more delay between the clock arrival. Hence, there is a clock tree, clock buffers, these are called buffers, right? As you can see, it's a kind of so to supply clock uniformly to all flops, the clock tree synthesis is done. That is one of the steps in a physical design. So these are too technical. In fact, we took these slides from the physical design course, and that's covered in detail along with labs. Now, in this case, I have taken and in a short time, see, for your information, clock tree is a 1-week module in the physical design course. Floor plan is 1-week module. Power plan 1 week. Placement is 1 week. Each is a 1 week. So now to cover that in half an hour, 1 hour, along with the demo is not easy, and not easy to understand also. So try to understand to the extent possible, get a feel of. So now when you put these gates into a physical dimensions of width and height, as you can see in the in the right side image, you can see some DFF. DFF means D flip-flop. Now your D flip-flop, there is no more a D flip-flop symbol. This is a width and height, and your pins are connected now with a clock. Your VDD is connected, your VSS is connected, your reset is connected, your D and Q outputs are connected. Though we are not able to show here, perhaps you will be able to appreciate in the. So signal connectivity for different pins as per your logic or circuit is nothing but routing. It's a signal routing. Physical verification is whether your design is manufactured properly as per the width and the kind of is nothing but physical design, physical verification. Then you need to check your frequency, STA, timing throughout the design, throughout the physical design flow at every stage. That's nothing but static timing analysis. This step verifies that whether your design is still working at that frequency or not. let's say if the design has to run at 2 gigahertz, is it still working at 2 gigahertz or not? It will ensure at every stage, because without which your chip, there's no use, because it will not run at a certain frequency. You can't use that chip. You can use it, but for which it is designed, you can't, you say new version, right? So hence, to ensure that it works at that frequency, we check the timing at every stage. So challenges, in fact, physical design is a challenging role. Too many new problems will come as per the technology. Let's say with a new process, the number of transistors per unit area doubles. So there is as per Moore's law, right? Every 18 months, your transistors in a given area is doubled, right? So same area, your transistors are doubled every 18 months or a year or 18 months, which means your technology is shrinking and shrinking and shrinking. Then the congestion, because it's a kind of a real estate has become costly now. Even a silicon more shrinking, more chips has to be made in a shorter space, so that your cost per chip will come down. That is the logic here. So that volume production is possible. In volume production, chip unit cost of the chip is less. That is the intent. And hence the typical challenges in the physical designer, your design is congested. Congested means in a given area, it's like a Bombay. You have a very limited, your real estate is very costly. Within 600 square feet, 800 square feet, you people live as a 2-bedroom. But in other cities, a double bedroom is 13 and 11 and 1,000 square feet, 1,300 square feet. That is normal. But in Bombay, 500, 600, maybe 600 or 800 square feet. Because the real estate is very costly. Or New York, if you take, it's very costly. And hence the buildings are, high-rise buildings are there in New York or in Bombay. Okay, sorry about that. Power, leakage power. And since these mobile processors should have a less, shouldn't, when you don't use it shouldn't leak the power. The battery shouldn't drain out quickly. Hence there are a lot of power optimization techniques are used, and that is a challenge. That is a challenge of late. That power optimization is a challenge. Reducing the battery life, increasing the battery life is always a challenge for VLSI engineers. Timing and frequency, increasing the frequency from 1 gigahertz to 1.5, even 100 megahertz or even 50 megahertz is not easy. So increasing the better frequency is a challenging for physical design engineers. Lower technologies, right? Your temperature inversion rules, the temperature inversion happens, and that challenges will be there. Area mixed signal design. So when sometimes the chips have analog and mixed signals also. So and runtime will be more. These are the challenges. And as the technology shrinks like this, you have associated challenges, particularly for physical design engineers. The RTL designers will not have, because they are in a software code level, and code level don't have much problems. And advances in CMOS fabrication, yes, lot of challenges, right? And because of the advancement in CMOS fabrication technology, it brings associated challenges. So advancement is happening in the fabrication technology, and hence it brings the associated challenges. And the software tools, EDA tools, has to be updated as per the, let's say, 7 nanometer to 5 nanometer or 3 nanometer. Now tools has to be updated accordingly. That is the difference between open source. Open source is who will update within 3 months, within 6 months or 1 year. So open source tools in a fabrication space, who will update in a time bound, is a challenge. Hence, practically very difficult to use open source tools in VLSI, particularly because it's a very high-end technology. Maybe simulation space, Verilog simulations, up to simulation or verification may be okay. But beyond that, once you go to fabrication part, so the tools are need to be updated in a time-bound manner to address the latest challenges. So these are the different advances happening. In the interest of time, I will be moving on because many of you itself need to know what is physical design. It's need to know the physical design itself. So I have a video here. Perhaps this itself is a 19 minutes or something. If depending on the time, this is a fabrication. Maybe how chip is fabricated. This is a Infineon fab or Infineon related. So I will skip this in the interest of time. I will come to that later. I will come to that later. Career opportunities for physical design engineers in VLSI. So that is about the. I didn't go into the because maybe I want to show you the demo. I want to show you the demo and then the what is the time now? Then career opportunities.
System or the tool. Every module has input and output, and the process is
fast forward here and show only the essential parts. So here what we have taken is we have taken up down counter, simple up down counter, 4-bit, 5-bit up down counter. No, the 8-bit counter. 8-bit counter, 8. Okay. So the 8-bit counter, and with the up down, where it will count up or count down depending on the signal, right? So that is and we will try to synthesize. Let me show the demo.
And that process is done in the terms of always at the begin of the operation. So here we are using if loop for just counting or incrementing or decrementing the values. So this is the process of the up down counter. So and then we end the module by saying end module terminology. If you have declared this, then the system or the tool or any script compiler can understand this Verilog code is ended by this line. So there the design stopped. So for this, we require actual access. And after
so I'm going now. So let's say that is the RTL. I'm forwarding now.
After entering DC underscore shell.
This is the tool for synthesizing. In a design synopsis design compiler is the tool, and we are synthesizing now.
Memory unit inside library files, which we can name it as link library, and where we need to create the used technology. So we are getting some technology cells or technologies from the one library, and we need to create another library for our own purpose, so that we can say it as target library.
Okay, so what I will do is, see, this is a script, Linux, these are Linux commands, and all VLSI works in a Linux environment. No more Windows. It's all, because the high-end, lot of computing intensive projects, these are computing intensive projects, and Windows servers can't handle, and the work happens in a Linux environment. So this is the script. Script means the commands to make the run works. So the initial part is the libraries. You provide the libraries, then the read file, Verilog file you will be reading here. Then you will analyze, then set the operating conditions, at what operating conditions your chip will work. Extreme, as what is the high temperature, voltage and process, what is the lowest temperature and voltage process, it's called best case and worst case. Then the source inputs SDC is the frequency at which your design should work. And this compile command does the conversion from RTL code to gate level netlist. So now I will fast forward wherever it is, with that. After that, you will.
After this,
After that, we will save the design.
There are few steps which we focus on. Reading the counter file. See, this is the RTL file which we give as input. So that input can be
So where is my cursor?
Made understood by the tool.
I am trying to find, not seeing my cursor. Okay, I got it. Okay, I'll fast forward here. I'll show wherever needed. And so he is sourcing the scripts now because the showing manually will take time. And sourcing means basically, see, let me play here. See, either you type the...
We have scripts folder where this particular file is located.
So, right? So it is loading the different technology, 14 nanometer. This is the libraries from 14 nanometer foundry technologies. So this chip counter we wanted to manufacture at 14 nanometer technology. When you give the technology libraries, the tool will convert your RTL code into 14 nanometer gate level, at least at a synthesis level, because this is a synthesis process. So the tool will do all the optimizations and conversions and mapping to a technology library like this using a design compiler tool. And this is a industry standard leader, worldwide leader design compiler is there for a synthesis purpose. So it will do like this. And see, it is doing different clock gating, registers. Registers are nothing but flops, for your information. In VLSI, it's called registers. Okay, so I will fast forward and it is completed. Now run is completed. We call runs. So the synthesis is completed.
Now we can see after running through the entire tickle file, after executing the file, we can see the outputs are saved in the specific directory of outputs folder. And the reports are also got saved. The entire design optimization is complete. So now we can check the files that we got as an output of synthesis. We are looking at two major outputs, which is one gate level netlist. Second one is synthesized SDC timing constraints as per the schematic that we require. And for looking the schematic, we can actually open the GUI, graphic user interface, and look into the schematic version of it. So this is the up-down counter, and you can see how these gates are laid out and how these are connected at the schematic level. But this is just a representation. It is not the actual functioning design. It is just a representation.
Yeah, as you can see, right, this is a gate level netlist. Means how your gates are, your counter, up-down counter are connected. Gates are connected, your flip-flops, your AND gate, OR gate, inverter, how they are connected with the different signal. There are inputs, there are outputs, there are different signals connecting the different gates. This is a schematic level representation of the design. So our input was an RTL code, as you have seen in one page RTL code, but our output is into the gates. Now let's see how at a file level it will look, at text level how the output will look like. So
this is actually the representation of the schematic of RTL file. So you can see how these cells are connected and how are the input pins given and how are the outputs driven out. So this is one output and these are outputs. Let us zoom into this. And this schematic is combinedly viewed as single block or single module, which is nothing but up-down counter.
See, this is a chip level. Let's say for us, up-down counter is a chip. It has a different signals. It has a up-down input signal. There is a clock signal. There is an enable signal. There is a flag. There is a reset on the input. The outputs are out 1, out 2, and out 1, out 2 are 5-bit each, whichever is a bus. This is the chip level. But if you go inside, you have a different gates connected and all of that. So the goal is to manufacturing this up-down counter as a chip in a particular foundry, 14 nanometer technology in this case of a particular foundry. So then there is certain process to be followed. Let's see now. Okay, so what we will do, we'll stop here. Now you have seen how a synthesis process works using design compiler. Now the output of this synthesis is a gate level netlist and a SDC timing constraint file, which will be used for physical design tool, and we'll come to that demo a little later. If you can share that demo video, we can definitely share after the thing. We will send a link for the demo videos so that you can take a look at it. Any student tools? No production tools. It's all, as I said, the point is industry doesn't have a time to train on some, again you on some tool. They want is if you are trained on certain tool as used in the industry, then you are ready for project. Now some tool where it is not used in the industry, they feel like training you again and they don't have that tool, and again you on certain thing, and the company doesn't have a time to for you to ramp up. Hence there is a generally they prefers people to get trained on whatever they need. So that is the trend in the industry. So the tools that you discussed, they are for RTL GDS or schematic to GDS. I think these tools, synthesis is RTL to netlist, and physical design ICC2, that will be gate level to GDS. In other words, RTL to GDS flow. Not schematic to GDS is a analog approach. Schematic to GDS is a analog. Let's say you have a PLL, you have analog to digital converter, when you have analog design, then schematic to GDS, that is a different analog flow. But I'm referring to digital flow. Isn't it the only PDK that need to be updated and the tools remain the same? No. Okay, so the analog flow and digital flow is different. Analog flow uses PDKs, digital flow uses libraries, and what you typically use in your college is PDKs and Cadence Virtuoso tool is a analog schematic editor. Cadence Virtuoso is a layout editor. These are the which you typically use in the college. But the physical design, that is analog layout. You can do a layout for analog designs. You can do a design in a schematic editor and layout in analog designs, but not physical design. Physical design tools, Cadence physical design tool is called Innovus. You need that Innovus tool. Demo video can share the link. Please share this. Okay. So I'll go back to, I hope the video might have been downloaded. No, I think it's not downloaded yet. I will go to my presentation, and in the interest of time, I will continue and we'll come back to the demo a little later. So I'll come back to the demo, right? In the interest of time, I think the career opportunities for physical design engineers. Of course, the physical design I'm seeing is ever the hot skill in the market for last 20 years. I'm in the industry for 24 years. And even when there is a recession in the US, now there is a, the people are talking about recession, global and all of that. Even in this recession in 2001-2 time frame in the US, when the dot-com boom went down, but dot-com boom and subsequent recession in US, there are still physical design jobs. When others are, doing layoffs and losing jobs, physical design has still jobs. Means the people available on physical design always very limited. You don't find training institutes also proper using industry standard tools available and offer physical designing is also very less. So physical design is enjoying demand consistently for last 20 years is what I'm seeing. It is only increasing and increasing. And hence on top of it, India is promoting, Indian government is promoting, wanted to have a fabrication fabs in India and have a lot of incentives, and that is expected to give, of course, fabrication and manufacturing related jobs, but the domestic, thankfully, design jobs are already there, for us. Overall, Indian ecosystem, government push and opportunities and incentives very encouraging. We are only hoping that it will further open up the opportunities for in the manufacturing side, packaging, testing, different other in the cycle. Currently, we are only doing design. India only design house for the semiconductors, but other, let's say, testing, packaging, board level testing, different, other skill sets, other jobs are expected to be created in the Indian electronics sector. Now, what skills required for a PD engineer? Good analytical and reasoning skills. I mean, good communication, good attitude. You will see the same thing for any VLSI engineer, any software engineer. You go to any IT company, also will expect the same. That's a minimum required for an engineer. If you are an engineer, you are expected to solve the engineering problems. You have to supposed to have certain skills. Otherwise, you are not an engineer, right? You're supposed to have certain creativity, certain analytical thinking, problem solving skills, and you should have communication skills, which is a must. So it is same as any other professional skills or any other engineer skills required for an engineer. But when it comes to physical design engineer, because you are a technical side, right? Strong fundamentals on digital CMOS, etc. is needed, because we are talking about ultimately CMOS fabrication, CMOS transistors, then and they are gates, nothing but AND gate, NAND gate, all the gates. Thankfully for a VLSI, right, it's enough VLSI if you know two subjects thoroughly. One is a digital subject, other is you should know the CMOS transistors, the electronic devices and circuits, and particularly on transistor operation, CMOS transistor operation end to end, top to bottom, everything you should know, because ultimately CMOS transistors are used in the VLSI. These two are a must, and for a VLSI engineer, it's a must. And strong conceptual knowledge on physical design. Then if you are a trained, then you should know the flow, the techniques, and the tools usage, standard tools usage in a physical design. These are the typical companies in India. I think I will skip this, maybe how to pursue a career in VLSI by now. Rather, some of you have run through these slides already, in the previous webinar. I believe you also have enough clarity on how to get into. In the interest of time, I will skip. So for physical design engineer, right, this is what physical design. If you need to be good in digital electronics, let's say, so you should be strong in digital electronics, you should be strong in CMOS devices. So you don't need a programming, whether C, C++, you don't need it. You don't need to be good in Verilog or System Verilog, none of the programming skills. It's a tool-driven job. You will be using the costly tools. You should be good at using the tools or softwares of the physical design software. That's the main work of a physical design engineer. And there are other specializations, analog layout. Analog is Cadence Virtuoso. Typically, why I'm saying Cadence is a market leader in the layout, in the analog space, schematic and layout. And hence your colleges also typically have a Cadence tools, and hence you might know Cadence very well, Virtuoso and all of that. And then there's a DFT, another specialization which handles the design for testability. Then there's a design verification, which I have already discussed with the name functional verification. Typically, the career progression, on the left side, it has a very good growth. Physical design engineers are highly paid in the market. I'm seeing that all the time. There are more number of jobs for physical design engineers, and even equal number of jobs for physical design and design verification. I have mentioned in the last webinar also. This has a more number of jobs. Next is that others are less. Analog layout, DFT, and others are typically less, but more number of jobs for physical design and design verification throughout. It is always because it's a more number of engineers are needed. Most common type of VLS engineers, I think I will just walk through this. Many types of engineers are there. You may only know PD, only it's called PD engineer or design engineer or verification engineer, but this many engineers are there in VLSI industry. And these are other types of roles that are there in VLSI industry. And about chip edge, I believe you might know already a bit, so I will skip that a bit. So we have a digital and analog courses. It's not one or two courses. We have many courses, particularly many professionals. Some courses are meant for professionals only. They're not offered to freshers. So let's say low power using UPF, that is for physical design engineers. And synthesis, sign off, ST and LEs, it's for working professionals, not for freshers. Because if we offer to freshers, you don't understand. That's the problem. And hence we have a different courses for students and freshers, different courses for working professionals. We do have a courses for if you are a working professional, either teaching faculty or a IT professional. There's a separate batches, separately designed weekend batches for the professionals. And corporates, we have a customized programs for them. And as you can see in the website, these are the different courses for on the left side for students or freshers. For professionals, we have a much more courses for professionals. Prasad, can you take a walk through the remaining slides briefly, and then we'll come back to the questions. But looks like that demo will take time. If there is a time for possible, we'll see it. If not, we'll send the demo video to all. Then I will take the questions. Briefly complete it, please. I think the physical design, we have a course offering for 10 years. We are 10 years old. And from day one, we are offering physical design. We are known for physical design in the market. We are leaders in that space. We have the best trainers, best material, best tools in the market. Go ahead and please walk us through.
Thank you, Venkat. Just give me a minute, dear all. Just now, the various offerings which are there in the VLSI. What we are offering for different people at Chipage is one. We have three different segments. One is people who are still studying, and people who have just completed their engineering and who want to pursue their career in VLSI. For them, there is a first category where we start the course from the very basics to the little complex one. And these courses are both on weekends and weekdays. And we also provide the placement assistance along with the mentorship where trainers will train them on the lab, how to use and how to complete the projects. And this, for students and freshers, we have the course which is integrated with internships. So that is an important aspect where you will be able to do the internship and you will get, one is course completion. After the course completion, you will also do the internship. So you will get course completion certificate and a letter for internship as well. So the entire course is of 5 months. And second category is for working professionals who are currently working in different departments who are related to the electronics engineering field. So they might be the faculties in some colleges, they might be working in IT sector, or they might be in some other vertical like sales or marketing where they want to come to the core domain of VLSI. For them, we have a separate course where we conduct this during the weekends, so they can also join and they can complete the projects here and get certified. And the third comes is the corporates, where corporate companies reach out to us and they request us to train their new hired, and we train them and ensure that they are in line with that organization's requirements. So these are the courses in the chip edge, that is physical design, design for test, and design for design verification. We have in all the categories, and for freshers and students, it is 5 months, and working professionals and self-learning mode. We also have a self-learning videos where you can go through the videos and understand the concepts well. and you can subscribe for that in case if you are interested. So we also have specific videos for RTL design and synthesis sign-off STA and RTL lint and CDC checks using Spyglass. So VLSI certification courses for students, we have courses which are starting in next few days. The first course starts on the 19th of Jan. That is for physical design, and then comes the design verification, where the course starts on 30th Jan. And the third one is design for test, which will start on 8th of Feb. And every course, as I said, it would be for 5 months with integrated internships. So you can complete your internships as well while you are studying if you are a student. So the mode of training in Chipage would be always the live online sessions. And apart from the normal trainers who are from the Chipage end, we also invite industry experts who will give you the training on every Sunday between 9:30 to 1 o'clock. So this will get you aligned to the industry requirements much more better. And then we also provide the live lab sessions where the instructors will suggest you how to do that and how to execute what you have learned in the theory. Then we also have the instructor-led live sessions, where we clear all the doubts, and the timings are given on the screen. It will be from 5 to 5:30 at 3 days a week, and lab training will be 3 days a week, 5:30 to 6:30 for entire 1 hour. And after that, then you can access the lab and practice what you were taught about. And this is available for 5 days a week on all the weekdays. So about placement assistance, which I spoke earlier, that we know that a lot of investment of money, time, you have invested in this to ensure that you get those skills which will enable you to get the best job in the VLSI industries. And we strive hard to ensure that you are well equipped skill wise, and we provide various supports to you which will enable you to face the interviews much more confidently. Like soft skill training will be there, and mock interviews will be there. This will be conducted by the industry experts who actually screen the candidates. So we call them and ask them to conduct the mock interviews, which will enable you to prepare yourselves. And soft skill training will be done by the corporate soft skill trainers themselves. And as I said, the mock interviews are from the senior industry professionals who are usually interviewing the candidates regularly. So how the integrated internship I was talking about a few minutes back, how we have designed this integrated internship is what I wanted to explain quickly. The first one is the learning phase, which will have 4 months of time where you will be trained well, along with the hands-on lab, as I already told you. Every weekday in the evening from 6:30 to 8:30, you will be having that hands-on lab, and this will be there for 4 months. And phase 2 will be the application and the projects of the projects. This will be for 1 month. This is here you will be able to apply the skills which you have gained in these first 4 months. And one project will be the part of your course itself, and the other project, the second project, will be the part of your internship. So apart from this integrated internship, the internship comes absolutely at no cost. We are not charging anybody any money there. People who are going for the course will, all the students will be automatically included into the internship. But however, any of the students say that they don't want to do the internship, they just want to complete the course, that is also okay. So how we deliver this course to you? As we said, each topic you will be briefed upon, explained, and trained, and then the lab sessions will be there, which will bring that practical implementation of what you learned as a theory. And we use synopsis tools there. And we also provide the trainer support where you can post your doubts to the trainers and the lab assistants through the WhatsApp group or emails. There are various methods where you can directly reach out to them. And yes, in during this 5 months of training, if you miss out any of the classes for any reason, you might not be well, or you might be having your exams in between, or you might be having internals in between. There, you can always go after your exams. You can go back and go for the recorded sessions of these videos. That access will be there with each one of the each student who has enrolled. And the overall highlights of the course is, as I said, one is integrated internship. Second one is placement assistance, which will enable you to apply for the job while you are in seventh or eighth sem itself, so that by the time when you complete your engineering, you will have more of the options open. And if you have done well in the interviews, then definitely you will have a job also in hand. So this placement assistance is also complimentary. We are not charging anything for placement assistance. We support because many of the companies are tied up with us, who reach out to us for various open positions in their company, and they seek the trained students of chip edge because they trust on chip edge to that extent. So, as I said, the next point about the course, the main advantage of the course is it is delivered by industry experts who knows what industry needs better. And 70% of your time will be on labs. This will enable you to have that hands-on experience, which will give you much more confidence while you face interviews, which will enable you to explain things thoroughly to the interviewer. And the last point is synopsis tools, which Venkat said are really highly in demand in the industry and one of the market leaders in EDA. So the synopsis tools are being used, and you will get the best hands-on training. So as I said, the synopsis tools are used, and various tool details are given in the slide here. In the interest of time, I'm just moving on. Certifications, Chipesh technology. We also, once you complete the course, seeing your attendance, how you did your, how you participated in your course, and what you understood, because there will be module-wise assignments and quizzes which you will take. This is your performance there, and there will be a final written test as well, and final project will be there as a part of your course. You will get the course completion certificate if you are able to get this through thoroughly. And this itself will prepare you better for the interviews. It will give you a lot of confidence while you face the interviews. Second is the grade will be given basis the performance, how you performed in the test. However, grade will be known to you. We will disclose it to the companies which hire you if they demand, or else we will not share that grade to them. If some of the companies ask for that, to whom we share that, because we believe in transparency. But yes, if some companies don't ask, we will not share it proactively. And then the internship letter, which is most important thing, or most important aspect of this student course, is they will get the internship letter, which you can show it to your college as well, where you have done the internship, and they can get that verified also with us, your college authorities. So who can join? Yes, probably Venkat already covered, and these things were covered in the previous webinar. So BE, BTech with ECE or EEE or instrumentation, and MTech students with VLSI or embedded or power electronics, and fresh graduates who have completed the ENC engineering in ENC, but are want to upskill themselves and get themselves ready for VLSI field. They can also go for this course, and MSc Electronics final year students can also go for this course. So these are our upcoming webinars. So one is the design verification. There is a webinar which, like how Venkat covered till now for physical design, you will also get the design verification and the career opportunities in design verification field, and it will be led by one of the industry experienced person on the 4th of Jan 2023. And then on the 9th of Jan, we have another webinar, which are free, and you will also get the participation certificate for this webinar. And there the DFT scope and SOC design and career opportunities in DFT will be there is a webinar on that on 9th of Jan, which will be led by one of the highly experienced DFT engineers in the VLSI industry. And my request to each one of you to please visit our website and go to the resources field, go to the webinar section, and you can register yourselves. And in case at any if you want to know more about these courses that we offer, you can and you might be a student or fresher, or even you might be working somewhere and you want to know about internships, please do visit our office, which is given here. We are located at 7th sector HSR layout, Bangalore, or you can call at 844-844-8839. Our learning advisors will definitely help you out on that, or you can email me at prasad@chipage.com. So that's all from my end.
Okay. So stay there. So let that be there. Okay. So in the interest of time, now I think we'll look at the few more questions, remaining questions. Now you can ask whatever questions you have. And we are already, it's 8 o'clock, 9. We are already over shooted beyond 8. So there are not many questions, means questions are answered at different stages. So we don't need much time now. So let me answer the remaining questions, whatever are there. Komal, are your courses online and offline? I think currently after COVID, right? Pre-COVID, we were doing offline classes. After COVID, we stopped offering offline. Now we will be starting offline again from this July. Currently, all the courses are online, hybrid model, blended models, etc. All the courses are blended models, etc. But however, now people are talking about COVID. Now we don't know how July situation will be, whether offline will start, or not. So currently, it is all online. It is running. All online means live virtual, self-learning. But most of them are live in an online mode. Do we have placements? Of course, placements were discussed. That's from Mohammed. Is there any 2 months internship on VLSI? No, I think we are not we do have, by the way, I think we haven't informed you. We have a development company called Celton Semiconductors. Perhaps Prasad, we should have included a slide on that. We have a Celton Semiconductors. Best performers will be hired for that development company, service company. So for a training level, we are offering, knowledge plus learning plus practice through a integrated internship. And we don't have anything 2 months. It's a 5 months only integrated with the course. Other than that, we don't have any 2 months, 3 months certificate. We don't have any other models because it requires certain effort to learn and do the projects. Without project, we will not give internship certificate. How can I register for the course? Yeah, please check in our website and call that numbers or fill any form and discuss with our learning advisors. Will help you with the further details. Looking for more such webinars would be great if you share these 2 demo links. Komal, demo links will definitely share of the synthesis. You can go through in detail. Prasad, please see that demo links are emailed to all participants. Registered participants, attended participants, both demos. The other demo is still downloading. So all other details, course related details, please discuss with our learning advisor. They will be able to provide. I think in the interest of time, let me go to check with charts. If any other, I think already posted there. 2 months internship and all that. Yeah, so Puranjit, can we do the course with our MTech college curriculum? Yes, that is the point, right? Now This course are designed. The classwork is outside office hours. The industry trainers take the sessions on Sundays, right? And hence, weekdays it is after office hours at 5:30, kind of 5:30 to 6:30, and then so it is outside the curriculum only, not in the college hours, because some of you have a classwork, and hence this is designed in that model. So it is well integrated. Particularly MTech, you have a lot of time. You can use that and practice in the weekdays and other times. It's a good option for MTech students to take this course. So if you don't have one more last question, something came. Python or TCL scripting, which is more preferred in future for PD? Is it as much as coding or small commands? No, so TCL scripting is required for working with the tool, and Python is a data related, handling data. Both are required. TCL is a must. Python is good to have, so that if you have each has its own strengths and merits. If you know both, you can master that. You can get command on the VLSI. These two applications are different. TCL is more tool oriented. Python is more data, big files, big data, all of that. To handle huge data with the Python will be very useful. Both are required in a way. Salary growth, Rajkumar, salary growth in a service versus product for 1 to 10 years. Salary will grow. That is not a problem. Salary growth depends on your knowledge. Salary growth will depends on knowledge, whether you work for a service company or product company. After particularly first 3 years, you have to invest for learning. After 3 years onwards, the salaries will grow year on year as per the performance and whether service companies or product companies, more or less they are comparable. Of course, initially product companies offer more, but after 5-6 years, more or less they both stabilize the same. Sometimes product companies offer stock options and all of that, which will be more attractive. Okay, this is what. Wait a minute. I think did it. Wait a minute.
Let us look into the.
Oh, okay.
Yeah.
No, I think the demo got downloaded and it is playing, but that's okay. In the interest of time, we will send anyway. You can go through the fees related, anything course related, right? That is more towards the specifics, and you please speak to our learning advisors. They will help you on anything related to the course. And you want to speak to any of the previous students or who got jobs or whatever, you can also do that. All that can help. Anything related to the career or course or a field, you can ask. Now, in the interest of time, we are already for 15 minutes past. Let's wrap it up. Thank you everyone for attending this webinar. Appreciate it. I think looks like what we are realizing is perhaps evening 6:30. Can you give this feedback? We felt evening 6:30 is a better time for students because after college hours. But if you keep on Saturday second half, we felt you still may have a college. Some of the colleges still have a second half. This one Sunday you want a holiday. At least one day you want a holiday. Which day do you think is 6:30? Do you think is a good time? Or what time from a student point of view will the webinars? Let's say many people could not attend because around 250 people. Many people could not attend. Can you please type in chat? What do you think is 6:30 as a good time, or it should be what time from your as a student perspective will be a good. So Komal, 6:30 is fine because we kept it outside college hours. Any other, is 6:30 good, or what is your? Of course, some of you who are serious about it joined, but many could not join because maybe evening. Any other feedbacks on 6:30 time? For anything related to course fees details, please speak to our just fill a form or call the number on the website, ChipEdge website. our learning advisors will help with the course related things. Yeah. So with that, appreciate everyone. Thank you for your time. For your patience. Unfortunately, we could not show the demo. I think since it came in the last minute, I could not download it. Now it came, but it's too late. So we will email you the demo video of physical design. Yeah. So whoever has any queries, please contact that number on the chat. Our toll-free number. It's normal number, and they will provide you. Thank you. With that, we can end the session, and all the best for your VLSI career, and whoever are in the campus or outside the campus, and best wishes. Thank you. Now,
Thank you
Prasad,
all.
I think we can close.
Yeah. Thank you all, and wish you a fantastic new year ahead, and a Merry Christmas to you. And please do connect to us for any queries. We will be more than happy to help you out on that.
And I think the other important is you are welcome to attend to other sessions to understand what is the design verification, what is DFT, and you or your friends can attend to know a little more about what is that specialization about. Okay. Yeah. Thank you.
Only
We
one
can
thing that I
close that
wanted to
session.
tell in the end is you will also receive the participation certificate on your mail after this webinar. So you can check your mailboxes post this webinar. Probably that would be there in your inbox.
Yeah, on the it would have been a good if in a 3-4 hours session is there, we could show live, we can give a demo. But in a 1.5 hour, not much can be done, because you have to know what is VLSI to physical design and demo. That's too much in a short time. Unfortunately, time constraints has limited us. Otherwise, an half day to 1 day workshop would have been good. So to show you the practical side of the physical design, we could have given a demo and answered and show you a flavor of it. Okay. Unfortunately, we could not show the demo due to limitations. We'll send the video. Thank you. Thank you, everyone.
Thank you all. We will connect again. Thanks a lot.